Hello, this is a brief introduction to Verilog. I got these slides from the internet. I would like to give credit to Professor Tamas Raikovich from the Department of Measurement and Information Systems, Faculty of Electrical Engineering and Informatics, Budapest University of Technology and Economics. Although there is a BME-MIT, the MIT does not stand for Massachusetts Institute of Technology, but it is for measurements and informatics information systems. So what is Verilog? Verilog is a hardware description language. So hardware description languages have been developed for modeling and simulating hardware functions. Only part of the language elements can be used for design implementation. Difference between standard programming languages and hardware description languages. Standard programming languages are sequential. What does it mean sequential? It means like if you have a list of statements, they are going to be executed one after one. So this is the normal programming like C, C++, whatever you have seen as programming languages. And they always go in like a thread. You go from one point and then you go to the next and next and next. HDL, no, it's not the same thing. That's what they are called hardware description languages. You're describing something that is hardware. So hardware exists in parallel. So if you have 20 transistors, if you power them up, the 20 transistors are going to start working, right? So they are inherently parallel. They are by construction parallel. So HDLs, they describe parallel and concurrent behavior. Concurrent means something that's happening at the same time. So you have two important HDLs, Verilog, which is the one that we're going to study, and VHDL. Actually, Verilog is covering more than 80% of the design. Like 80% of the people in design are using Verilog. VHDL is I don't know a lot of people using VHDL, but still some. Right. Verilog language uses a hierarchical functional unit-based design approach. What does functional unit? It means you are describing the functionality of the hardware. You are describing the hardware functionality. And it's hierarchical. It means you start from a module that contains a module, that contains another module, etc. So this is an illustration of that. So you have the ALU that has the add, sub, multiply, and divide, and then you have a mux, and then you get the result. So here you are deciding about the operation, and then you have the input for the operands, right? Verilog module, definition of the input and output ports, definition of the logical relationship between the input and output ports. Modules, top-level modules, the top-level module. Its ports are connected to the I/O pins of the hardware device. Like the top level, it means the highest hierarchical. If you know about the Russian dolls are actually toys or decoration toys that one Russian doll contains the other and contains the other, etc. So the outer one is the top level module. It's like the one that contains all the other modules. So module definition syntax, for any module you have the keyword module and then the module name, like you give it some name, and then parentheses, and then the operands, the port list. It's not the operands, the ports, the IOs. So you have input, or you have a keyword wire, which is optional, and then the size by using bits, and then the name. So you have port declarations after that and description of the functionality. So port declarations will go in detail more. And then you have the keyword end module. Every module should be terminated with an end module. And it's better to put modules in the same file with the same name of the module .v. So this is a convention. You can put many modules in the same file, it doesn't matter, but generally people do that. They use one module per file. So port declaration syntax. The port declaration, you have a direction, data type, size, and port name. Direction is either input for an input port, an output for output port, and in-out for bidirectional. What does bidirectional? Is like something where data can move from outside to inside or from inside to outside. and it depends on the functionality. So in-out is basically very rarely used, especially in FPGA. I've never seen in-out, very, very rarely, because it's bus based, and buses are not very well described in CMOS. They are not very, very friendly to CMOS technology. That is the main technology, that's the only technology I know of that FPGA are realized with. Data type. Wire is the default data type when omitted. So wire is always omitted, right? Behaves as its name says. It's a wire. It's just a wire. A reg means this is only for outputs. A reg, which does not always become a real register, is used for outputs when outputs are registers. So you can see that input wire OP1, but wire is omitted always. And output reg. Sometimes you do output directly, which means it is a wire, or output reg, which is it is a register. And register is not going to be necessarily generated as a flip-flop. As we learned last time, the synthesizer will decide depending on the way you describe it. And the size is between J and I. So this is like square bracket, J, colon, and I, and then closing square bracket. So the size is absolute value of J minus I plus 1. So the rightmost bit is the jth bit. The leftmost bit is the ith bit. So leftmost means the LSB, and rightmost is the MSB. I think it's the opposite. So the rightmost here is like, depending on how you visualize your register, but if we see the slide, J is on the left and I is on the right, so don't be confused about that. Alternative module definition syntax. Ports can be declared in the port list. This is since Verilog 2000, they are supporting this. Before 2000, I was using it. This was not supported, but you can, instead of having something like this, like you have the port and then the port declaration, you merge that in the same thing. The only difference is like here you have commas separating rather than semicolons. The commas separating the statements. That's it. Internal signal declaration syntax. This is the same as the port declaration, but there is no direction specification. The data cannot be omitted. Examples: 1-bit wire, which is wire counter enable, or a 16-bit register, which is reg 1520 counter. So this is a 16-bit register, right? So you have to declare some pieces inside your module that are like given names to some wires. You have to name every single wire. You cannot use wires that are unnamed. Yeah, the constant definition syntax. So you have bit number, a tick, and then number system, and then constant. The bit number is the size of the constant in bits. The default size is 32 bits when omitted. So number systems, decimal is the default if omitted. So binary, use the letter B for the number system, for decimal D, for hexadecimal H, and for octal O, but nobody is using octal. You can use underscore character to separate the digits, just for clarity of reading, for easier for us to read, stuff like on 8 bits, you have 4 bits first, then underscore, then 4 bits. If you don't use underscore, you think this is a different constant. And here, if you don't have the 8 tick B prefix, you will think this is decimal. So underscore is very important. So this is value 4, decimal value 4. This is 6 dash H, which is hexadecimal 1F, means this is a hexadecimal digit, this is hexadecimal digit, this is a 6-bit hexadecimal constant. Why 6? Because we said 6 bits at the beginning, and decimal value is 31. 128 is a decimal constant the right away. So if you write 128, it's just a decimal constant. Parameter definition syntax. So you can use parameters. What is a parameter? Parameter is something that is not gonna have a variable value during operation. Like a wire is something that can take 0 or 1, depends on what is happening. So wire is a real piece of hardware. A register is a real piece of hardware, but the parameter is not. Parameter is a constant. Parameter is a constant, but it's a constant that exists before implementation, before simulation. So if you are doing simulation, it exists before simulation. So this is what it means. So you have two kinds. You have parameter, a parameter that can be overridden from outside when instantiating the module, and the local param that cannot be overridden. So its value is gonna be there locally. Parameter definitions can depend on each other, which is the advantage. The parameter name can be used as a constant in the module where the parameter is declared. So normal parameters, their default value can be changed when the module is instantiated. This is what I'm talking about, this kind parameter. And local parameters, their value cannot be changed, right? But indirectly, you can define a local parameter as a function of a parameter. So you can say local parameter equal alpha equal beta minus 2. So beta minus 2, beta is a parameter that was defined earlier, parameter beta equal 3, for instance. All right. So here this illustrates the use of a variable width kind of. The width is not variable when your circuit is running. Is variable when you are instantiating it, right? Is you create a generic counter, say, okay, I want it to be 8-bit here, I want it to be 16-bit in some other place, I want it to be 32 bits in some other place. You don't need to change the code. You just instantiate it with a different parameter. We're gonna see how we do that. So this is an alternate module definition syntax with normal parameter that can be declared in the module header. So we can do that. It's just you use a pound before the parenthesis. Pound parenthesis means the list of parameter, and then you close the parenthesis for that, and then you open another parenthesis for the IOs. Now we're gonna see some operators. This is the concatenator operator. So concatenation operator, what does concatenation mean? It means you are appending some bits together. So you take 3 bits, 4 bits, and 7 bits. 3 bits, 4 bits, and 7 bits. You put them together, they will become 3 plus 4 plus 7. 3 plus 4, 7, 7 plus 7, 14. So that's an example. Here we have 5 bits and 2 bits and 1 bit. 5 plus 2, 7 plus 1, 8. So the result is going to be 8 bits. This is not statement in Verilog. This is just showing you what does it mean. This is what it means. Writing this in your code or writing this, they are exactly the same. The advantage is like sometimes you put a variable here, which is completely legal. Here also you can use this to create multiples, like to create repetition. So instead of writing 101 again, 101 and 101, you write 3 times 3 bits 101. That's what it is. Importing use cases. The sign extension. What is the sign extension? The sign bit actually on a constant is always the MSB. So if you want to change the length of this constant, change the length, you go from 4 bit to 8 bits, you are going to do sign extension. This is the sign extension statement. You are doing an assign statement as 8 bits. You want it to be the same thing, but with the sign extension. So as 4 bits and with the sign bit repeated 4 times. What does it mean repeated 4 times? If the sign bit here, if S 4 bit of 3 is 1, then you want all of these 4 bits to be 1, so that you have 1, 1, 1, 1, and then 1, and then the rest 3 bits. If the sign bit is 0, then all of these are going to be 0, so 0, 0, 0, 0, 0, and then the remaining 3 bits. So you just represented the same value with the sign extension, with just very simple technique. So the masking of a vector, right? So masking a vector with a single bit, the small operand is bit extended with zeros if one operand shorter than the other. So if you have data which is a 4-bit vector, a 4-bit, 4-bit wire, like 4 wires, a vector of 4 wires, and then you cannot say data and enable, because enable is only 1 bit. You are going to enable every bit with a repetition of 4 enables. You are taking the wire and copying it 4 times. So this is what it means. Remember, this is a hardware description language. You are copying the wire 4 times, which we're connecting 4 wires to 1 wire, which is the same name. But this is what it means. And doing an AND operation between them. So bitwise operator. What is a bitwise operator? It's like they operate on bit by bit. So operate by bit by bit. So a number of operands, this is the not, and not is the tilde. This is the not symbol. This is the and symbol, this is the or symbol, and this is the XOR symbol. Number of operands, not has only 1 operand, and or XOR have 2 operands. If the operands are vectors, the operation is executed bitwise, so they have to be the same size. If one operand is shorter than the other, the shorter operand is bit extended with zeros to match size, always. If this is not desired, use the concat. If you don't want them, if you don't want this behavior, right, you have to extend everything with zeros. You have to use the concatenation operator to match the size. Example, if you do 4 bits or 4 bits, you get 4 bits. So this is an OR. 0 or 1 is 1. 1 or 0 is 1. 0 or 0 is 0. And 0 or 1 is 1. Negation, if you flip the bits, all the bits of an 8-bit, it's like you are using 8 inverters. That's what it is. So these are the bitwise operator. The logical operators are different. The logical operators, they are trying to calculate a logic. So a logic is the result of a logic is always true or false. True or false. So the number of operands, not is 1 and or is 2. Always yield a single bit value, 0 or 1. Examples. So you have 0, 0, 0, 0 or 0, 1, 1, 1. One of them is 1, so the result is 1. Here you don't find any operation bitwise that is 1, then the result is going to be 0. And negation of 4 0 is 1. That's what it is. In some implementation, it just look at the last digit, especially in C. Verilog is built on top of C, so the underlying implementation of the Verilog compiler or the Verilog program that interpret Verilog languages is C and C++. Bit reduction operators. What is bit reduction? You are going to do an operation with all the bits of the same value. So here, and 4B0101. So you do 0 and 1 and 0 and 1. So 0. So you are doing bit reduction. This is the OR. The result is always going to be 1. Yield the 1-bit result 0 or 1. Arithmetic operators. These are very simple. Plus, minus, multiply, and divide, and modulo. Number of operands 2. Divide and modulus operators are synthesizable only if the right side operand is a power of 2. So this is in standard Verilog. But there are some special compilers that will actually do the division, create a divisor, and they will tell you to select that. But they are rare. In general, they are correct. This statement is correct. If the divisor is a power of 2, then it is going to be just shifts. Shift operators. Left shift and right shift. What is a shift operator? You are just shifting the contents by a certain number. So here if you have 8B0011 underscore 1100, you shift by 2. You move everything to the right by 2 positions. So these 2 zeros are going to disappear and the last 4 bits are going to be 1111. And the upper 20 are going to be injected. These upper 20 have been injected. These ones, not the B. Yeah. Same thing, this is going left. Same thing, you are going to move the inject 2 bits here. So this is shift right and this is shift left. Relational operators. This is check for equality. This is check for inequality. This is check for less than, greater than. So less than and greater than, they are arithmetic. Everything is numbers in Verilog. Everything is numbers. So everything you have registers are all binary and numbers. This is less than or equal. This is greater than or equal. Number of operands always 2 and yields a single bit value 0 or 1. So examples, this is less than this. 1011 is less than 0111. No, that's not true. So the value is 0. This is 1011 different than 0111. That's true. Then the value, the outcome is going to be 1. Conditional operator. This conditional operator is for an expression. It's like a multiplexer. The conditional expression is first evaluated. So you have conditional expression, conditional operator, and then expression 1, and then colon expression 2. And then this is the expression. And then you can embed that, and then it can be in many different statements. But this is conditional operator. The conditional expression is first evaluated. If the result is true, non-zero, expression 1 is chosen, is evaluated. If the result is false, expression 2 is chosen. So that's conditional operator. Selecting a part of a vector. So vector name of I and vector name of ji. I select the ith bit of the vector. You can access a vector, just a single bit from the vector. You can access a subset of bits from a range subset range from the whole vector. So if you have a vector of 15 to 0, you can access the bits 2 to 5. So you say v of 5 colon 2, like that. You have the freedom to use that in your code. Assigning value to wire type signals. What is an assign statement? The assign statement is an important statement in Verilog. So this is the most basic. What you are saying I am connecting an expression which is a combination of some wires and operators to a wire signal. So this is permanent connection. So you cannot have two assign statements where the target variable is the same. It is wrong in Verilog because as if you are telling him connect to two different things at the same time. It does not make sense. So this is the idea. So the expression is evaluated and its value is assigned to wire signal all the time. Example, you have 3 wires of 16 bits. So you are doing assign C is equal A and B. So every single bit of C is going to be the bit of A ended with the bit of B, right? That's what it is. Since they are the same size, there is no issue. Assigning value to reg type signals. Value can be assigned to reg type signals in always blocks using the this operator. So you cannot use the assign keyword to assign values to reg, only to wires. In the reg, you do it in always blocks, and we will understand what is an always block later. Always block. Always blocks. Always block is like a block that is the most important block in Verilog. It is there to help you create combinational blocks or sequential blocks. What is a combinational? Is something that contains like gates right without any flip-flop. Sequential is something that contains gates and flip-flops. So like something you want it to be a flip-flop. So that's what it is. So always arrow-basque, or this is like the at sign, the at character, sensitivity list. What is sensitivity list? Is like a list of variables and methods for which you are going to reevaluate this always block when you are going to change the variables that are modified by this always block. So the sensitivity list determines the events when the assignment are evaluated. So it means here always at A, B, C. It means anytime A changes, B changes, or C changes, this always block is going to be evaluated. This is anytime that anything changes, this is going to be evaluated. So star means anything. And this is at any time that there is the rising edge of the clock. Post edge is a Verilog keyword. Rising edge of the clock, you evaluate. This means here you want to create flip-flops. Here you are meaning to create flip-flops. Here always at neg edge of clock, post edge of reset. Means here you are having reset, you are having flip-flops with reset where your reset is not synchronous, is asynchronous. Asynchronous reset, not synchronous. Here you can have a reset that is synchronous, that depends only on the clock. Most reset in the FPGA, they are synchronous, so you use this method. You don't use this. You know, very rarely people use this. Okay. Value can be assigned to a reg type signal in only one always block. You cannot, it's like you are defining a flip-flop with one set of hardware things connected to it. You cannot have two flip-flops with two different circuits and they have the same name. That does not make sense. And you are telling the tool, oh yeah, they are the same flip-flop, but they are connected to two different things, and then we will have a conflict. What should I assign? So that's why this is a value can be assigned to a reg type signal in only one always block. If, else, and case instructions can be used only in always blocks. They cannot be used outside. And multiple statements must be grouped using begin and end keywords. Example, so you hear what you are doing. You are having something declared as reg. Reg does not mean flip-flop necessarily, but means something that you use inside an always block. You cannot use a wire inside the always block as the target of assignment. So here what you are doing C is every time A or B changes, change the value of C and always make it A and B. And D, make it A or B. So that's what you are saying, describing here, in the same always block. And this is called non-blocking assignment, means this assigning things to C and D happen in pure parallelism. Pure parallelism. So they are saying you cannot do that. Always at star begin C, B XOR D. You cannot have an other always statement where C is assigned again. You cannot have another one. That's what it means. It means this, you already mentioned C here, you cannot have C in another always block. That's what it means. If instruction, syntax. The if expression and statement one finished, that is terminated by a semicolon, and then else statement 2 terminated by a semicolon. The expression is evaluated first. If it is true, non-zero, statement 1 is executed. If it is false, statement 2 is executed if you have an else statement. Sometimes you just have an if without else statement, so it do nothing. So this is what is said here. The else pass is optional, it can be omitted. Multiple statements must be grouped using begin and end keywords. That's as for other statements. The case statement. What is a case statement? Is actually multiple ifs that are happening at the same time. So this is the case, expression, alternative 1, alternative 2, etc., and then statement 1, statement 2, and then default statement. The expression is compared to the alternatives in the order that they are written. Their order can mean priority. For the first alternative that matches the corresponding statement, is executed. If none of the alternatives matches, the default statement is executed, the default keyword. Multiple statements must be grouped using begin and end keywords. Module instantiation. What is a module instantiation? It's like you are defining a module, and inside this module you use some other module. So you use it, you are going to create a copy of this module. A module is like a model, it's like a definition of how this should work. But the instance is like a real circuit. It's like you say, I make it real, I create it, I am making it real, I am instantiating it. You can create modules that are never instantiated, they will never be part of the simulation if you don't instantiate them anywhere, right? But the minute you instantiate them, then their existence becomes meaningful. So you have the module to be instantiated. This is, you defined it somewhere in another file, and then this is in a different file where you are using it. So you have wire DEF, some wires, and then you have the name of the module, okay, the name of the module, or the model, the module identifier, and here you have the instance name, because you can, in the same file, you can instantiate different multiple copies of the same module, multiple copies, but they are different circuits, right? You connect them differently, you have the freedom to do what you want. So you want to create, for instance, 10 different counters, and they use the same model. One counter is for counting, I don't know, like counting numbers, number of cars, some counters for counting number of people in the car, some counters, anything. So you have the ability to instantiate the same module several times. So that's why you need different name. But the instance name should be unique for the same module. Should be unique per module. Here the way you connect. So here you can see input A. So in order to connect A to F, you do dot A parenthesis F. And you are doing dot B parenthesis E. You are connecting E to B. So E is your wires inside this module, and B is your port. C is the port. So this is how you are connecting them. The module to be instantiated, that's another example with parameters. So here what you do, you are having some function that has 3 ports and 2 parameters. So you want to change the value of the parameter. So you see that in the definition, you will say P1 is equal to 8 and P2 is equal to 16. Here once you are instantiating this module in some other module, you are deciding, oh, I want P1 to be 3 and P2 to be 20. And I'm connecting A to F and B to E and C to D. You do what you want. So here you are overriding, like you are forcing the new values on the parameter. And of course, the parameters here will have new values all throughout all the use. Wherever P1 appears is going to be replaced by 3, not 8. And wherever P2 appears is going to be replaced by 20, not 16. Example 2-to-1 multiplexer. This is an example where we are describing a 2-to-1 multiplexer. So select one of its input signals and outputs that to a single line. So they're just a 2 input, and then the inputs are single bit and the outputs are actually 1 bit as well. So you have a selection line, and this is the implementation. So we are deciding to do the implementation. So this is one way of doing it using gates. So the operation, if cell is 0, then in 0 is connected to out. If cell is 1, in 1 is connected to out. So it means that if cell is 0, then this is inverted. Then this is going to be 1, 1 and 1, or 0 and whatever is 0. So this is in 0 going out. In 0 or 0 is going to be in 0. So this is how it is described. So in 0 and not cell, or in 1 and cell. That's as simple as that. So this is the whole module. So you have max 2-to-1 8 bits. So this is an 8-bit version. Max 2-to-1 8 bits. And this is input wire 7 to 0 in 0. Input wire 7 to 0 in 1. And input wire selection wire is only 1 bit, always, because it's 0 or 1. And output, you have 8-bit output. So you do simply assign out in 0 and 8 cell, 8 times the non-selection, or in 1 and 8 times the selection. So using the same gate implementation. So this is using the bitwise operator. This is not a good idea because the described function cannot be determined easily. Like you cannot read it and send this is a max easily. Like if you use this, we'll show you a different technique. A simpler technique is to use the conditional operator, this operator. The interface is the same. So out is cell. If cell is 1, then in 1. If cell is 0, then in 0. That's much simpler, and it is a natural max, a natural description of a max. Or you can use an always statement, but in this case, the output should be declared as reg, because you cannot use wires inside the inside set. And then you have the if statement. If cell is equal to 0, then assign in 0 to out, else assign in 1 to out. And since this is the start, or whenever any input changes, then the output is going to change. Or the selection changes, then the output is going to change. So another one using the case statement. So this is very important because this you will see how much possibilities you have to describe the same thing. So using the case statement, you do case cell, because the selection is the thing that it's changing, and then it's 1B0 and 1B1. Here you don't have the default because you covered all the binary cases. If you have a case statement where you don't cover all the possibilities for the variable that is between parentheses for the case statement, then you need the default case to say that if none of them is, if it is not equal to none of them, then you use the default statement. But here the default has no meaning. You can see, as simple as that. Now we are doing 8-bit 4-to-1 multiplexer with 2-bit selection. So this is a 4-to-1 multiplexer. What does it mean? It means we have 4 inputs. In this case, we are using the default statement. This is what I was talking about. So here you have, if it is 0, 1, then use send in 1 out. If it is 1, 0, send in 2 out. If it is 1, 1, send in 3 out. But if it is default, means 0, 0 in this case. But just to show you how it works, we could have used 0, 0 directly, and this will not have a default. But because we did not cover all the possible cases and only 0, 0 is missing in this case, then we are using this. And this will close our first part of the Verilog series. Thank you very much, and have a good day.